So today I am going to talk you through a very simple example of how we can perform sulfide saturation and sulfate saturation calculations using a new Python tool, PySulfSat. So what we're going to do is first you're going to navigate to the PySulfSat read the docs page here. And what you can see is there's a lot of information here, so you can click on various things of these. You can click on information about units, or each one of these examples is a Jupyter notebook, which you can look through. So we're going to run this locally. So what we're going to do is we're going to click this View in NB Viewer, and then we are going to click this Download button, and that will download it into your downloads on your computer. You then want to click on this link, and this will take you to GitHub. And again, this is an Excel spreadsheet that you're loading in, so you're going to want to download this and put it in your Downloads folder. You're then going to want to copy that into some folder somewhere on your computer. Here I have made a folder called YouTube, and I'm just going to show you what that Excel file looks like. So many of you will recognise this is the standard output from Petrolog3. So once you've downloaded all of that, you need to launch Jupyter Lab or Jupyter Notebook, however you do that on your computer. If you're new to Python, I would recommend doing that through Anaconda. And then we're just going to go to kernel, and we're going to restart kernel and clear all outputs, and that will clear everything so that it's fresh on your computer. So this is your file structure on the left, so make sure you're in the folder, and then this is the Jupyter notebook you downloaded. So if this is your first time using PySulfSat, you're going to want to uncomment this and then run this cell. You can use Shift-Enter, or you can press the Run key. I already have this on my computer, so once you install it once, you don't need to install it again. You just need to upgrade it, and there's information on that on the Read the Docs page. Then we import NumPy, Pandas, and Matplotlib. This allows us to do math and plotting. And then we import PySulfSat as SS. Then what we're going to do is we're going to use the PySulfSat import data function. We tell it the name of the spreadsheet, and in this case, we're telling it this is a Petrolog file. This means it goes through and it knows what Petrolog headings to look like, and it converts them into the format that we need for this Python tool. So you can see we're printing the first 5 rows here using the head function. So it's reformatted all the data, and then all of the Petrolog columns that you inputted are further along. So you can scroll along here. So first off, we're going to do the simplest possible SCSS calculation. We're going to use the model of Smythe 2017, and we do that using calculate S2017 SCSS. We give the function the data frame that we loaded here. So this is this thing called data frame out. We tell it a temperature in Kelvin, and that is in here. So basically what we're doing is we're saying a data frame and then square brackets with quotes means that's a column name, so a column in that data frame. Same for pressure in kilobars. We're then specifying an Fe3, Fe total liquid column. Again, Petrolog has that. And then the final thing is the Smythe model is sensitive to the ratio of iron over iron, nickel and copper in the sulfide. So here, for simplicity, we're using a fixed value. This was measured by EDS on the SCM by Weiser et al. 2019. So we can run that. And what we can see is that it has calculated the SCSS ideal for Smythe. It's calculated the error value, and then it's appended kind of all the intermediate calculations as well as all of the inputted columns. So everything is in there if you want it. You can see if you want the non-ideal SCSS, you would also have to put these as inputs. So for example, you might measure that as 0.1 on the SCM, and that'll give you both the ideal and the non-ideal SCSS. So this is the data frame. It has the calculation and sort of the major element data. So the first thing we can do is we can make a plot, and here we're making a plot with 2 subplots side by side. Again, we're using this pandas notation of the data frame name, a square bracket, a quote mark, and then the column name. So we're plotting the iron content of the liquid versus the ideal SCSS. And then we're also plotting the SCSS plus the 1 sigma error and the SCSS minus the 1 sigma error. And then we're doing the same, but on the x-axis now we are plotting magnesium. So this allows you to look at changes in the SCSS during fractional crystallization. Instead of using the Smythe model, or as well, you might want to use the Hugh O'Neill 2021 model. This is pretty much exactly the same input, so we can just run this. You can see this column is the calculated SCSS, and all of the intermediate calculations are here. So now we might want to add the O'Neill model to our plot to compare how Smythe and O'Neill compare. So here O'Neill is shown in blue and Smythe is shown in red. Okay, say you want to use the Li and Zhang 2022 SCSS model. Same, the only difference is this name in the function is now Li and Zhang. So you can run that, and again, it's calculated the SCSS total. Or you might want to use the 14 model. This does not account for the sulfide composition, but it does account for the water content. So you can either specify the water content in your data frame by putting the column like this, or you can specify it as a fixed value. Say you had to run your Petrolog calculation at different water content because the phase appearance was wrong if you use the accurate water content. Here we can reset all the calculations to run at 3% water. Now, what you might want to do is you might want to compare the SCSS trajectory, which is the total amount of S2- that can dissolve, versus what would happen to sulfur if it was behaving completely incompatibly in the melt. So this uses the function crystallize sulfide incompatible. You have to give it an initial sulfur content, so this might be from looking at melt inclusion trends. And then you have to give it the proportion of the melt. So here, this is stored in the melt % magma column of Petrolog. And we can just run this and you can see it returns a pandas series of sulfur increasing with fractional crystallization. So let's plot all of these, the Smythe, the O'Neill, the Li and Zhang, and this kind of incompatible model. So you can see that if you were just pretending sulfur didn't saturate in a sulfide phase, you would expect it to increase with decreasing magnesium, whereas if your magma is sulfide saturated, you would expect it to decrease with magnesium. And you've done all of this in kind of a few seconds. You can plot this in different ways. You could plot it against magnesium and iron across the entire fractional crystallization range if you wanted to. In reality, in many systems, you will not know your sulfide composition. You will not have been able to make measurements on the SEM. Perhaps you don't have an SEM, perhaps you don't have the samples and you're looking at literature data. So we can also use different ways of calculating the sulfide composition. So Hugh O'Neill in his 2021 paper has an empirical parameterization based on the nickel and copper content of the liquid, which predicts the ratio of iron over iron plus magnesium and copper in the sulfide. So here we are using the Smythe SCSS model with the sulfide composition calculated with Hugh O'Neill. So to do this, we also need to supply an input for the nickel and copper content of the melt. You can use the Petrolog input. The problem is if you have a lot of sulfide, that will start becoming incorrect because Petrolog is assuming these elements behaving incompatibly, whereas actually you're stripping them out. So often at this point, it is better to produce some sort of empirical fit through nickel and copper data, or you could use PySulfSat to build your own kind of like iterative removal model. So those are all options, but just simply showing you how this would work. So here you have the SCSS, and you have the ratio of the iron over iron nickel copper it has predicted in the sulfide. Dwayne Smythe has a more complicated method of calculating sulfide composition. This is based on basically iteration of you start with a copper and nickel content in the sulfide, you then calculate a KD using Cassiva, which is a function of iron and temperature, and then you use that to compare to the nickel and copper content of the liquid for the KD, and you kind of converge down until you get the minimum mismatch between sort of the calculated and the real KD partitioning between sulfide and liquid. So there's more detail about that in the paper, but very simply here we're using the same SCSS model, but now we're using the Smythe way of calculating sulfide composition. So you can see, you can scroll along, and here is the calculated iron and nickel in the sulfide. So we can plot this now. This is very similar to how we were plotting things, but now we're using the calculated sulfide value. And you can also, most importantly, plot the sulfide composition that's being predicted by these models. So green is the O'Neill 2021, yes, and then this one is the Smythe sulfide. So this should be S 2017 calc sulfide. So you can see that the measured sulfide composition in the system is shown in red, so 0.65 approximately. So the Smythe sulfide really underpredicts the iron over iron, nickel and copper ratio, and the O'Neill model works reasonably well between sort of 2 and 6 weight percent, which is kind of where it's calibrated. So this isn't a great surprise. So this does show that you do need to be really careful and inspect the calculated sulfide composition, because it can go very far off your measured sulfide composition, high and low magnesium. So you also wanted to calculate the SCAS. This would be a bit of a weird thing to do given this Petrolog model was for Hawaii, but this can be important, particularly when you start correcting for sulfur 6+, which we're going to do in another video. So very simply, we use the function calculate and then the name of the model and then underscore SCAS. You don't need pressure, you don't need FE3, FET for these, so you have less inputs than for the SCSS models. So you can run that, and if you want to know what these functions are doing or what any functions are doing at any point, you can do help like this, and it will tell you that this is using the model of Chowdhury and Dasgupta. And then it kind of tells you the things that are required or not required for this model. So we can look and we can see that the calculated SCSAS in these compositions is extremely high, about 22,000 ppm. So we can plot the SCAS against iron and sort of magnesium if we wanted to. And here we're showing the, so if you want to know what the other one is, you would do help and then this, so you can find out what these functions do. So this is Zajac and Say 2022 SCAS model. So you can see they give pretty different results. We're plotting one as blue, one as red here, and there's weight percent SCAS on the y-axis. So if you just want to plot that second one, which predicts much lower values, you could just plot that rather than having the y-axis being overwhelmed with the first model. The final thing you might want to do is calculate the amount of sulfide which has formed along your fractional crystallization path. So again, you can run the help fraction to see how this calculate mass frac sulfide works. So it tells you you need to give it a sulfur model, so that's maybe your SCSS, your SCAS, depending on what system you're in, or the SCSS corrected for sulfur 6+, which again we'll do in a different video. You need to tell it the initial content of your sulfur in the melt. You need to tell it a proxy for the amount of melt left at each step and the sulfur content of the sulfide in ppm. So here the melt fraction is from Petrolog. We're starting with 1,600 ppm sulfur, and we're saying there's 32 weight percent sulfur in the sulfide, and we want to use the O'Neill fixed sulfide model, so that's the sulfide that we measured. So you can run that and calculate the mass fraction of sulfur, and then you can plot this against magnesium or any other parameter. So if you scroll through this notebook, the rest of the way you will find some examples of correcting for sulfur 6+ and different ways to convert between redox buffers, etc. But we are going to cover that in a second video, so that's it for now.